gains some angular momentum. So that gain in angular momentum comes from some loss in angular momentum, and that loss must be reflected in the angular momentum of the electromagnetic waves. So now coming back here, we found the linear momentum density. So in terms of the linear momentum density, how can I express the angular momentum due to an infinitesimal volume? So if you just consider an infinitesimal volume here at a position described by a vector r, which you can just express it in terms of the radial component. So at that position, if I am interested in finding the angular momentum in the electromagnetic field, infinitesimal angular momentum, to find that, first I need to express the angular momentum density. So the angular momentum density L EM is going to be, and EM is going to be R crossed with rho EM. So rho EM is given by that. And R, I can express it as S along S hat. You agree? So this is gonna be, I'm talking about at some point R, which I described by SS hat, crossed with rho EM, which is that mu naught Q N I over 2 pi S times by L with the minus V. All right. So what do you get when you take the cross product of this? Huh?
Yes, cancels.
Yes, S cancels, and you get LEM equals to mu naught Q Ni over 2 pi L S crossed with P, that gives me Z. We need to have the minus sign, right? All right, so that's the density. Then what's going to be the total angular momentum? So LEM, all you have to do is you have to integrate the density over the volume, right? So this should be minus mu naught Q N I over 2 pi L, the 2 pi L of the integral of d tau z hat, right? So integral of d tau gives you what? The volume. So what should be the volume of the region where you have a non-zero electromagnetic angular momentum density. So what should be that? EM equals to minus mu naught Q N I over 2 pi L. So how can I express the volume? Yes, pi times r squared minus A squared times the length N. That gives you the volume. Along the z-hat direction. So that would lead you so LEM equals to minus mu naught Q N I over 2 pi. Well, pi cancels out, so we have 2. Yes, R squared minus A squared along the. So the rate of change of angular momentum for the fields is going to be, if you calculate dLEM by dt, what you'll find is the change is due to the change in current, right? So you have minus mu naught N Q R squared minus S squared over 2 di by dt along with the other direction. So that tells you that the electromagnetic field angular momentum is decreasing by this rate, while the cylinder is gaining at the same rate, because we showed it's positive for the angular momentum of the cylinder. So the rotation of the cylinder comes from the transfer of angular momentum carried by the fields into the cylinder. So if you want to find the transfer angular momentum, then all you have to do is do the integration while the current goes from some value I naught to 0. So if that's going to be EM, is going to be minus mu naught NQ over R squared minus A squared over 2 DI. So if I integrate this, I'm interested in the gain of the angular momentum by the cylinder, so that initially it was not rotating, so now it's rotating, so it goes from 0 to, or I think it should be, if I want to find the angular momentum lost by the electromagnetic field as we decrease the current, so it should be L EM, that was the initial, let's say when there was a current I, and to 0, and this one should be from what to what? From I out whatever initial value to 0. So this would give you an EM that's going to be the minus sign, and this is going to be minus mu naught N Q R squared minus A squared over 2 I naught and dr.
Would you lose the negative sign on the right hand side?
Yeah, so minus becomes 0, minus I naught, the minus sign becomes plus, so that's going to be EM is going to be minus. So if you do the same thing for the cylinder, then you would find a positive value.